So kind of a question about, let's see what happens with E1 versus SN1. So at this point, right, we always say the first question we ask ourselves is what type of alkyl halide do we have? So let's just say, for an example, I'm going to go with this. And we'll say we're doing it in isopropanol. Right? So the first question we always ask ourselves is what kind of alkyl halide do we have? So in this case, we have a tertiary benzylic. Right? So tertiary benzylic, so we know tertiary benzylic. That narrows it down. We know it can't be SN2 then, because tertiary doesn't work for SN2. So at this point we are down to E1, E2, SN1. Right? I'll draw SN2 on here and we cross it off. So like literally to start these you could draw, I mean one of the things you could do is write E1, E2, SN1, SN2. Right? And as you eliminate one, just cross it off. Right? So tertiary, it can never be SN2, so we'll cross that off. So we're still stuck here with these other three. So then we ask ourselves, how reactive is our nucleophile or base? So in this case, we look and we see isopropanol. There's no negative charge, so that's not super reactive. So that would automatically probably eliminate E2, right? Because E2 likes reactive bases and polar to apolar solvents too. So now you're down to E1 and SN1, right? So the first step in either case, right, is going to be carbocation formation. But how do we think about debating which one is better at this point, right? Trying to figure out which one's better. So let's just look at the products of both. What would the products be for both? So the first step is the same either way, right? We're going to form a carbocation. So there's a tertiary benzylic carbocation. That's really good and stable. Right? So that's good. Now, either our solvent here, the isopropanol, is going to be a nucleophile or it's going to be a base. One thing I would ask right now though is, so for an E1 reaction, right? For E2, we really worried about being anti-periplanar. Do we care about any of that in an E1 reaction?
No.
No. So stereochemistry for an E1 reaction, we don't worry about anti-periplanar. Because right, you form a carbocation, now you can essentially eliminate from either side. So you don't need to worry about the anti-periplanar conformation with an E1. So if it was an SN1, let's see, I'll draw I'll assume that we can do the mechanism. And I'll also assume, so I'll draw the SN1 product here. What the heck, I'll draw it out. Let's go in there. So the first step, there would be, and of course the rate determining step is a carbocation formation. We'd have Br minus of colors floating around as well. But now we have this H plus charge here. Our Br minus is floating around. Br minus would take that. And then our final product here, kind of looping back around here, would be this ether. Then we'd made HBr, and of course, another solvent could have grabbed this proton too, but HBr is a strong acid, it's going to dissociate. So there's the SN1 product. Cool. I don't have any real strong feelings either way, right? One of the things you look at, say, is it reactive or not? Right, so we said that this isopropanol is not very reactive. Is it super big? Right. The other question we ask ourselves is super bulky. It's not super bulky, right? It's not a tert detox either. It's not an extra method, so it's not super big. So SN1 is possible, I'd say. But let's look at the E1 product and maybe say, wait a second, this E1 product is maybe really good. So I move all this stuff up a little bit. I'm going to redraw that first initial carbocation intermediate. And now when we do an E1, just like when we do an E2, we got to find beta hydrogens. So the carbocation in this case is the alpha carbon, so these would be, beta hydrogens here and beta hydrogens here. So let's draw those in. And so for every type of beta hydrogen we have, that's a different product we could have. So we have a choice to make here. Are we going to choose these beta hydrogens, A? We're going to choose this guy, B. Well, I would choose B because it's going to be more substituted, but A would be less up. But both cases, either case, both double bonds would be what? They would both be conjugated. They would both be conjugated, right? If I put an alkene here, it would be conjugated in the system. If I put an alkene here, it would also be conjugated in the system. Right? They're both conjugated. So if they're both conjugated, which is more important than Zaitsev's rule. So if they're both conjugated, that's good. So if we have a choice, let's make the most substituted one. And that one's going to be taking the beta hydrogen off of B. So let's take a look at that product. Of course, there's Br minus still floating around. So now you can see here, right, this double bond is conjugated into this system, right? This sp2 carbon is right next to this other sp2 carbon. They're all part of the pi system. And that would have been a case if I would have gone this way too, but it would have been a less substituted alkene. So now, right, if this is our E1 product, and this is our SN1 product, when I look at these, right, that E1 product looks awfully good with that conjugated pi bond. So I would probably say the E1 product's more likely than the SN1 product. Not to say that the SN1 product's not likely at all, not going to happen, but it's just not as likely as E1 in this case, right? So conjugation really counts for a lot, right? And that only happens with the eliminations, right? So sometimes you have to look at the products to see which is most stable, which is the better product. So in this case, I would say E1. So let's also compare SN2 and E2. So in this case, let's go with something like this. So let's do E1, E2, SN1, SN2. I'd like to have those four there maybe. And I'll say, what first question is, what kind of alkyl halide do we have? In this case, we have what? Secondary allylic. That's right.
Which doesn't narrow it down.
Right. So does it work? Secondary allylic work for E1?
Yeah.
Sure, it does. Right. If you have a carbocation there, you can stabilize it with pi bond resonance. Does it work for E2? Yes. Everything works for E2. SN1, can you form a carbocation? Yes, you can. Pi bond resonance. SN2, secondary, still works. So everything works. Fantastic. So what kind of nucleophile we're going to use? I'm going to go with methoxide. So what kind of nucleophile is that? Is that reactive or unreactive? It's reactive. So right, I can even put down here DCM, right? Dichloromethane is a polar aprotic solvent. So it's a reactive nucleophile, so that eliminates who? E1's gone.
And SN1?
SN1's gone. So now we're down to SN2 and E2. So the next question we usually ask ourselves is, right, how bulky is the base or nucleophile? Is it big, small?
Pretty small.
This one's pretty small. So we certainly think SN2 is still possible, right? If it was really big, it wouldn't be able to do SN2. But just because it's small doesn't mean it can't do E2. So again, it's kind of got to get to the point where we have to look at the products. What do the products look like? And try to debate what's good there. So easiest one to do, I'll do the SN2 mechanism first because that's pretty easy. So SN2 product is going to look like, right, and really if I'd done stereochemistry, right, that's an asymmetric center, isn't it? It's four different things bound to sp3 hybridized carbon, yeah, good. So I could even added that layer on there if I wanted to, but I didn't. So there's the SN2 product. and we also make Br minus. Fair enough. Let's redraw it again to do the E2 mechanism. E2, we always have to look for what? Beta hydrogens. So let's draw those in. So I think there's a beta carbon, and those are the beta hydrogens. There's also a beta hydrogen over here. So there's how many? There's two types of beta hydrogen, but how many of them matter? So only if this is A, and these guys are B. Which ones matter, A or B? B, because A, remember, A can't line up essentially, and you'd make an it's weird. Don't do it. You'd make an alene, and that's a little more complicated. So here, though, why would this take place? So if I use the blue now, take the H, right? It has to be anti-periplanar, but right, it doesn't matter in this case because again, there's no stereochemistry. And normally, if we in an E2 or E1 reaction, we'd rather make what kind of alkene? An E or Z?
E.
Which one? E. Yep, E. But in this case, does it matter? No, because right, we'd made this plus Br minus plus OH. Right, you made those three things. Okay, so that's the E1 pathway. So well, that's good. That's all conjugated. It's not, but they're all monosubstituted double bonds or alkenes, right? They're monosubstituted, so that's good. So like the case I just drew here, I bet there's a pretty solid mixture of the two things, right? Conjugation's good, but the nucleophile is still pretty small, so SN2 is probably going to take place too. So it's very unsatisfying. You're going to get a mixture of products, right? If I wanted to just get E2, oh gosh. If I wanted to just get E2, what could I do? What could I change? I could heat it up, right? They talk about heat makes a big difference. Make the base bigger. Make the base bulkier. That'd be another way to get more at that E2 product. Absolutely. But yeah, heat. Yep. I didn't talk much about that, but heat absolutely favors eliminations more. But yeah, bulk that base up a little bit. That would also get you more of that E2.
So substitution reactions want small.
Yep, because right, at the end of the day, right, you still have to get in there, right? Substitution, you really got to substitute out, especially for SN2, right? SN2, you got to get to sigma star. That's hard to get to. An empty p orbital in a carbocation for SN1 is easier to get at, right? It's flat. There's a top. You can attack from the top or the bottom. But SN2 is pretty, right? It's pretty tough to get at. That's harder ones to get at.
Is that the same as E1, E2?
Yeah. So
Or
right.
E1, SN.
So E1 and SN1 is the same idea, right? If you wanted to favor an E1, you'd bulk up the base, right? It wouldn't be, right? So reactivity is different, of course, than the size of the base, right? But if you want to favor elimination, always just make the base bigger. Bulk that up. That'll favor elimination always. So would, right, anything conjugated is always a good thing for eliminations as well. Big base, conjugated things, more substituted alkenes, that makes elimination more likely to happen.
So
All right, let's talk about non-ZFT products and how to get those. So when we talk about non-ZFT, we have to know you're talking about eliminations, right? Because ZFT refers to alkenes and pi bonds. So we're talking about eliminations for sure. And a good way to test here is like, do we know what ZFT's rule is, right? Well, if we're talking about non-ZFT stuff, we better know what ZFT means. Right, so ZFT's rule basically says the more substituted the alkene, then it is more stable. All right, so that's what ZFT's rule is. The more substituted the alkene, the more stable it is. But we don't always want the most substituted alkene. And sometimes we don't get that, and we have to explain why we don't get that. Right? So non-ZFT refers to getting the alkene that's not the most substituted then. Non-ZFT.
and it's only fluorine, right? Is the only halogen that.
Yep, so be careful. So we'll go through one at a time. So the first one should be obvious. Hopefully we already hit this. Conjugation is always more important than ZFT's rule. Right? So if you have the choice All right, in this case, 1, 2, 3, 4, 5, 6, 7. Where are the beta hydrogens at? Which carbons have beta hydrogens? 3 and 5. If we were worrying about Zaitse's rule, which hydrogen would we take? Where would we want the alkene to be?
3.
If we were worrying about Zaitse's rule.
Oh.
5. If we wanted, but in reality, what product are we going to get? We're going to get, and this doesn't matter if it's E, in this case it has to be E2, right? If I put a bulky base, we're only going to get this product. Oops, make sure I draw it right. I numbered my carbons for a reason here.
Because of conjugation.
Because conjugation is more important than Zaitse's rule. Also notice, I made a choice. What kind of alkene is this? E or Z? E. I could have drawn the Z one, right? But which one do you think is more likely? If I have a choice, I'm going to make the E. But remember, if you start seeing wedges and hatches, then you got to get things anti-planar lined up. But in this case, you don't see it, so you should go ahead and draw the E as the product. All right, so conjugation trumps Zaitse's rule. And also, this is a good time to remind yourself, if there is a discrepancy between E and Z, and there's no stereochemistry, no wedges and hatches, you always want to draw the E. Another good point here is to look at the base. So I chose a bulky base not because, right, well, sure, a bulky base would make it easier to get to this carbon because this is a disubstituted carbon versus a tertiary or trisubstituted carbon. But also I chose a bulky base so as to not have any SN2, right? Because this is still a secondary alkyl halide, right? And SN2 and E2 are both possible. So if I want to make sure, right? Again, if I want to make sure I only get elimination, I chose a bulky base, right? Just to absolutely make sure it's E2. Absolutely. All right. So the next factor goes back to that theme of bulkiness. If I have a tertiary alkyl halide and I have a very bulky base like this, or even heck, I can make it a monster, right? A really bulky base, but I certainly have a tertiary alkyl halide. Again, we look at our molecule and say, well, it's a tertiary alkyl halide. Where are our beta hydrogens at? If I number our carbons, which carbons have beta hydrogens? 1, 3, and 4. How many different types do I have? 2. 1 and 3 are the same. So now I have a tertiary alkyl halide, a big bulky base. It's going to be hard to get to, essentially it's going to be hard to get to this hydrogen on 4. Even though it leads to the Zaitsev product, the more substituted product of the double bond between 2 and 4, I can't get there because everything's just too big. Everything's in the way, right? It just won't work. So I'm going to go ahead and grab the most accessible H, which would be 1 or 3 in this case, and the product I make is the non-Zaitsev product. And this has to do with his sterics. Sterics is the big driving force here. Tertiary alkyl halide and a big bulky base is another way, right, to get the non-Zaitsev product and bulky base.
How do you determine what's bulky enough? 'Cause, like,
Anything
obviously the top one looks bulky.
Anything above this and higher is bulky. Tert butoxide is bulky. I just made this for, emphasis. I start throwing carbons on there. He's making it even worse. But yes, this I would consider bulky. Tert butoxide is bulky. All right, our third and final way to get the non-Zaitsev product is another E2 variant essentially. I guess essentially I would say the first two, the conjugation, the bulkiness, right? That can be both E1, E2, E1, E2, right? Because I said bulky base. I didn't say reactive or unreactive base. I said just bulky, a big base. So E1 and E2 could work for this. E1 and E2 could work for this one. Makes sense? That conjugation is good for E1 and E2. Bulky base, bulky alkyl halide, E1, E2 thing. This last one really only works for E2. So fluorine as a leaving group. So this isn't really an only E2 type phenomenon. The other ones work for E1, E2, both of them do. So I would say E1 and E2, and I would say, if I grab this and pull it down, pull everything down a little bit. This is also E1 and E2, right? E1 and E2 both want conjugated products. The bulkiness matters also for E1 and E2. But now fluorine's a little different. This is just really talking about E2 in this case. So let's draw a possible scenario. Whoops. So throw the fluorine on there. Like this. So fluorine's a leaving group. We look at the beta hydrogens. So 1, 2, 3, 4, 5. How many types of beta hydrogens does it have? 2. Which carbons?
1 and 4. Oh, 1 and 3.
1 and 3. Right? So obviously 1 is less substituted than 2. So what happens here in this case, and I told you it had to be E2, so let's just go, let's do our standard bulky terbutoxide base. It's going to be, the product you're going to get is the NonZFT product, so it's kind of giving it away a little bit here. So how's this going to work? So the hydrogen of 1 is the one that's going to be taken. So let's see why that is.
Is it because of how good fluorine is at, like how good of a leaving group it is?
Fluorine is a crappy leaving group. So it's not going to want to leave in one step. It's going to make you essentially form a carbanion and make you wait for it to leave. Okay. So actually, kicking the fluorine out is the slow step. So this is actually a mechanism called E1CB. But don't worry about that. We'll talk, if you're an advanced organic, you'll learn about it. Right, so you have this carbanion, and what do we learn about carbanions, right? It's just the opposite of carbocations. Carbocations, when you have a plus charge carbon, you want hyperconjugation, right? Because hyperconjugation gives you electron density from sigma bonds 2 bonds away. But if I have a negative charge, I don't want electron density, I have electron density. So it's just the opposite. You want to be less substituted. So why is the hydrogen and carbon 1 taken away? It's because that makes a carbanion that's less substituted, which is more stable. Right? So now once we have our carbanion, eventually fluorine finally relents and leaves. But what you end up with then is the non-ZFT product. Right? You get the alkene, the pi bond, that's not the most substituted. There you go. So those are 3 ways. And the last one's really only an E2 thing because it goes through a carbanion. So you really have to have a reactive base to get this one to go. Okay, so a retrosynthetic problem. Grand finale type stuff. So first step I would do, number your carbons. So let's number the product carbons usually first. 1, 2, 3, 4, 5, 6. Let's, and now the other one, right, if I'm guessing, right, carbon 2 and 3 have the alkene, the pi bond here. I'm going to guess that this is probably carbon 2 and maybe this is 3 and this is 1, right? Because where the functional group is at, like where the action's at, really doesn't change much in these, right? At least not too much at this point. But so if you look at this though, you should also recognize what looks like I added 3 carbons, at least, right? I added 3 C's. You should think about how many ways you know how to add carbons. Well, you know Grignards, but you also know, remember the alkyne way, the terminal alkynes? So I would be thinking, right, maybe something like this at some point, a terminal alkyne. You probably also notice this is a trans alkene, right? Trans alkene. How do I make those? That's the first question. And if you have an alkyne, how do you make alkynes too, right? Because we don't have an alkyne in our starting material or in our final products. We got to think about how we make alkynes too. And these are kind of notes I'd write to myself, right, when you're thinking about this, right? That way I can give you points for doing that. All right, so let's look one step back. So one step back, this is a trans alkene. What starting material can make a trans alkene? What is the starting material that does it? An alkyne. An alkyne. Right? Make sure our bond angles are good. All right. 1, 2, 3, 4, 5, 6. All right. We already noted over here an alkyne, right? We know we need to make. We need a terminal alkyne to make a carbon-carbon bond. Which carbon-carbon bond should we make going one step back here?
The 3 and the 4.
Between 3 and 4, I think. Good. Good. Now we have an alkyne. How do you make an alkyne? What star material can make an alkyne? To make an alkyne, how many pi bonds does an alkyne have? You guys you've been learning about eliminations. For every pi bond you make, you must have what? An elimination, and to do that elimination, you need what on your molecule? Beta hydrogens and a good leaving group, right? And we're going to learn later on, it doesn't have to just be a halogens. We're halogens right now. So we need beta hydrogens, we need good leaving groups. But we need how many here?
2.
So where should we put the 2 leaving groups at? Which carbons?
2 and 3.
Let's put them on 2 and 3. Actually, you could also put both of them on 2. Right? But we won't do that this time. Okay. Very good. One more step back. If I want to add 2 bromines, what starting material would that have came from? That's a reagent. Br2 is a reagent. So when I say starting material, I mean with carbon. I mean the carbon part.
Could you do like an alkene?
That's it. Absolutely. Do an alkene. And between which 2 carbons? What would the pi bond be? 2 and 3, right? Okay. To make an alkene, to make 1 pi bond, how many leaving groups do you need? 1. I think we're back to the start. Good. All right, let's go forward now. The blue. What reagent do I need to form that alkene there?
A good nucleophile.
A nucleophile?
No,
Base. A strong. Let's do a reactive base. So let's do the classic E2 tert butoxide base. Good. If I want to add 2 bromines, what reagent do I use? Alkene plus Br2. Good. If I want to lose 2 bromines, do a double elimination, what do I need? A strong base.
NaHH2.
And we've been using NaNH2. So you need how many equivalences? At least 2, right? Because you're doing 2 eliminations. Now, you could just put excess, because the next step, what are you doing? The next step, you're also taking this CH bond off of carbon 3. So you could say excess here, right? But I'm going to do it stepwise just because. So So I'll say step one, we need another thing of NaNH2. Right, 'cause that's gonna take off the H of carbon 3. You could have said excess, that'd been fine. Then step two, we need what? What do we need in step two?
Well, we need carbons 4, 5, and 6.
Right, and so where should I put which carbon needs to be delta plus? 4, 5, or 6?
4.
4. Good. So this is 5, 4, 6 out there. Good. All right? Do an SN2 there. Now the last step is to make an alkyne into a transalkene. What reagents do we use for that?
Could you just do HCl?
No, because HCl is going to add a chlorine then. Remember it's, nope, Lindlar's would give you the cis alkene. It's Na in that liquid ammonia, NH3. Right? Either lithium or sodium. Remember that one electron mechanism. Right? That's how we get that transalkene. Good, from an alkyne.